Welcome to High School Physics Explained, and today I want to go through the HSC paper for Physics 2018. Let's start now with the multiple choice section of the paper. So let's start by question number 1. A satellite orbits Earth as shown. Which diagram correctly shows the direction of the satellite's acceleration? Now you're probably familiar with most satellites moving in a circular orbit, and in this case we have an ellipse. Now a circle is simply a particular variant of an ellipse. That doesn't change the fact that the acceleration, that is the centripetal acceleration, is still going to always point towards the center. So the correct answer is always going to be A. Question B. Which graph is consistent with the predictions resulting from Planck's hypothesis regarding radiation from hot objects? And if you look, you've got 4 blackbody curves, but it's important to first appreciate what the axes are supposed to be. Now for this particular shape, wavelength is always on the x-axis, so automatically C and D are discounted. The important thing too is to know that as temperatures increase, the intensity increases by a large factor, in fact to the power of 4, and also the peak moves successively towards smaller wavelengths. Again, the only possible answer in that regard becomes B. Question number 3. The graph shows the altitude of the International Space Station during 2017, and the altitude can only be boosted by supply craft visiting the IS. Why does the altitude decrease in times between height boosts? So this is not about the supply craft. This is what happens in between visits. Now it's in low Earth orbit, which means it's going to encounter the atmosphere. First response momentum of the ISS is being transferred to the air molecules. What that means, of course, is that part A is suggesting that the momentum is going to decrease, therefore the velocity is going to decrease, causing the air particles to increase in their velocity and therefore increase the momentum. So we have a transfer of momentum. And a drop in velocity is going to cause a drop in altitude. So that seems to be correct. But let's confirm that with the answers that we have subsequently. The moon's gravity changes the net force on the IS station. The moon has nothing to do with it, so that is not correct. The decrease in altitude makes it possible for supply craft to reach IS. That may be true, but it doesn't tell us why it occurs, so C is out. And D, the total mass of the ISS changes with deliveries from each spacecraft. That is true, but the orbital velocity is going to be determined by the square root of gm/r, and this m is the mass of the Earth. The mass of the ISS is not a factor here, so as a result D becomes also incorrect. That again confirms A. Question number 4, we have a motor, a battery and ammeter are connected in series, and when the motor is turning at full speed, the ammeter has a reading of 0.1 amps. While the motor is spinning, a person holds the shaft of the motor to stop it. Which row table correctly identifies the change in the ammeter reading and explanation for this change? Well, the fact that we have a motor spinning in a magnetic field means it automatically has something called back EMF. That back EMF lowers the effective voltage. Therefore, if you have a lowering voltage, you then have the resulting current because of that. If you then stop it, you no longer have the changing flux, and as a result, you're no longer going to have the supply of the back EMF, which means the overall EMF increases, causing the current to increase. But I just told you we just removed the back EMF, so that can only be this response as a result, so the answer is D. For question 5, this is a mathematical question. The diagram shows a current carrying conductor in a magnetic field, and you have to determine the magnitude of the force on the conductor. This is a simple F is equal to BIL sine theta question. We want the force. We know B is equal to 1. We know I is provided. It is 2. L is the length, which is 0.05. And finally we have sine theta, and that is equal to sine 30, leaving a total result of 0.05 Newton, and therefore the answer becomes B. The diagram shows a saucepan on an induction cooktop. Which row of the table correctly identifies the property of the material used to make the saucepan and frequency of the changing magnetic field produced by the coil? Well, we need a rapidly changing flux in order to generate eddy currents, and those eddy currents will cause the metal to heat up, and as a result we have the heat being transferred into the saucepan. I need a rapidly changing flux. That means I need a high frequency. But the material must be able to conduct electricity, and so we need a conductor. And therefore, the only answer becomes B. For question number 7, a planet X is twice the mass and twice the radius of Earth. What is the magnitude of the gravitational acceleration close to the surface of the planet? G, of course, of the Earth is equal to Gm, which is the mass of the Earth, divided by r squared. We now have an object such as planet X, and in this case, G for planet X is going to be E. Now the mass, we're told here, is twice the mass, so it's 2m. And we have the radius, in this case, is twice the radius, so it becomes twice the radius all squared. And if I clean that up, you'll see that I get 4 pi r squared on the bottom, and I have 2gm over here, and therefore 2 and 4 cancel out such that we have 2 here, but I have gm over r squared, which is E. So we have, in essence, a half of the Earth is Gx, and that makes A the answer. Question number 8. Crystal lattice structures for 2 types of doped semiconductors and band gap diagrams are shown. And you have to determine which one is going to be talking about an N-type or a P-type, and we're looking at the band gap diagrams. If we have an N-type, we have a valence of 5 as our dopant, and if you look very carefully, we have 5 here. We have only 3 here. That automatically confirms that this must be an N-type because we have a dopant with a valence of 5, phosphorus being a good example. On this side, we have only 3 valence electrons, so we have the dopant, like boron, for example, with a valence of 3, and this is clearly a P-type. Going on this side, we have the conduction and valence band. Here we have a forbidden gap. That is classic of semiconductors. Here there is an overlap. That is not a semiconductor at all. That becomes a conductor. So Y is representing conductors, not even semiconductors. T is an N-type, and so that is true over here. U is a P-type, so that is true over here. But on this side, only X is the semiconductor. So therefore, B cannot be correct, and therefore D is the only possible answer. A hypothetical journey to a distant star might be accomplished in an astronaut's lifespan by travelling at relativistic speeds. What is the key concept which underpins such a hypothetical journey? There are 3 consequences of relativistic speeds, and that is time dilation, length contraction, and mass dilation, but from which frame of reference you're referring to. So let's have a look at the 4 responses. From the frame of reference of the spacecraft, making the journey, the distance to the star is less. So as far as the space person on the spacecraft is concerned, the universe has a certain length in the direction of travel, but because that is outside their frame of reference, it shortens, and so the distance becomes short. The universe contracts, so to speak, so this certainly sounds correct. Clocks on the spacecraft run slower, and hence the rate at which fuel is used for the journey decreased. But the important thing is that the clocks on the spacecraft only run slower outside the frame of reference. Since the fuel is on the spacecraft, and therefore you are measuring the time on the spacecraft, it's the same, so this is incorrect. Relativistic effects on the spacecraft reduce its mass. Well, that's totally incorrect. In fact, it increases its mass as long as you are outside its frame of reference, so that becomes clearly incorrect. And finally, the relativistic increase in the mass of the fuel on board makes it possible to complete a longer journey with less fuel. Well, again, it may increase fuel from the outside perspective, but in fact that's problematic because now you have increase in mass and fuel, and therefore much greater forces are required to get it to the speed. So that becomes incorrect as well, and so the only answer is clearly A. 10. The diagram shows some parts of a simple DC motor. Now you'll note that there is no split ring commutator, and I believe that is done on purpose, because you're supposed to understand that because it's a DC motor, it will have a split ring commutator, and the question clearly says only some parts are shown. Now the important thing is with a DC motor, as long as Wx remains perpendicular to the direction of the magnetic field, which it stays through the whole side as it turns on this particular side of the loop, the force is going to always be constant on that side. But then over here, with the split ring commutator, it changes direction and then remains constant on that side. And so therefore, C and D are the correct responses, at least from this perspective. The direction of the torque produced on the coil by the force. Well, the important thing about the split ring commutator is to ensure that this continues to turn in the same direction. Now, the magnitude of the torque does change, particularly in this situation when we clearly only have horizontal magnetic field lines. So it does fluctuate, but the question says the direction of the torque. So the whole purpose of the split ring commutator is to ensure the direction being constant. That means this response and this response, and that leaves you C as the correct answer. Question 11. During the launch of a space vehicle from Earth, an astronaut feels an increased downward G-force. Which of the following situations would a person also feel an increased downward force? Now, if you're looking for an increased downward G-force, you're feeling the expression, but it's actually as a result of the normal force pushing you up. So what you want is two forces of the normal pushing you up. In the case here, you are feeling a lot lighter. You are traveling in the downward direction, you're traveling with gravity, and so the normal forces that you experience, let's say at this point, is going to be less upwards because you are actually moving in the downward direction. So this is not correct. If this is traveling at a constant velocity, then of course the G-forces you're experiencing is 1G. If this was accelerating, as in speeding up, increasing in velocity, then you would have, like the spacecraft, feeling two forces, the reaction force of the surface here, and of course this is accelerating also upward. You're going to have the reaction force of simply your weight pushing it down, but you also have the floor pushing you up at an acceleration. That increases your G-forces. But this is a case where it's slowing down, so it's actually reversed, so therefore this is incorrect. This one's clearly incorrect because you're traveling at constant velocity, so the only G-forces you're going to be experiencing is simply one G-force. This one here is the case that's going to be correct, and I'll explain it. When this plane is, let's say, at this position, you have a force of gravity pulling you down, and you have a normal force on your backside pushing you upwards, and so that is going to be your G-force. But this plane is moving in a curve, and let's assume that this is a circular path. It looks parabolic, but the theory is still the same. You're now going to have an acceleration, a centripetal acceleration, if we assume that there's a bit of a circle here, also acting in that direction. So you're going to feel heavier, and so only then will this be the correct answer. Question 11 requires a little bit more mathematics. The diagram shows an electron traveling in a vacuum at 2 × 10 to the power of 6 between two charged metal plates at 1 × 10 to the -3 meters apart. And you're asked to work out a magnetic field that is going to be applied to this so that it travels continually in a straight line, and you have to determine the magnitude and direction of the magnetic field that is to be applied. So first of all, let's determine what the electric field is in between these plates. The electric field is going to be equal to the voltage divided by the distance. Since we have a potential difference of 1,000 and we have the distance between the plates as 1 × 10 to the -3, you get a value of 10 to the power 6 volts per meter. What direction is that electric field? Well, we have the positive plate, so we're going to have a value that is acting down in that direction. Now, with that in mind, that means my electron beams are going to experience a force in the upward direction if there was no magnetic field. So we need a force due to the magnetic field in the downward direction. Using your right hand and remembering your thumb represents the direction of the conventional current, that's going to be pointing in that direction, then you'll find that the only possible solution is a magnetic field that goes into the page. Only that will give a force that counteracts in the opposite direction. We now have established that it's going to go into the page. But what about the magnitude? We have our electric field value there. The force due to the electric field is simply equal to EQ. but the force due to the magnetic field is equal to QVB. They're going to be equal. And so if I rearrange that, I get that velocity is equal to the electric field strength divided by the magnetic field strength. Now we are given the velocity. The velocity is 2 by 10 to the power of 6. The electric field we've just worked out, that's also equal 10 to the power of 6. And of course, we have to work out B. If I rearrange that, B is equal to 10 to the power of 6 over 2 by 10 to the power of 6. I get a value of a half, and a half is equal to 5 by 10 to the power of -1 Tesla. That only gives me the answer of A. Now 13, we have a charge moving in a circular path because it's experiencing a centripetal force as a result. And of course that centripetal force is equal to mv squared over r. This centripetal force is also due to the magnetic field, which is going to be QVB. Now what would happen if my speed of my electron is increased? Well, this equation here tells you that if my speed is increased, let's say it doubles, that there is a direct relationship to the force that it experiences. It increases as well. So therefore, these are our only possible answers on this side. But if you look at this formula over here with the centripetal force, is that my speed doubles. Remember that my force therefore also has to double as well. What we'll do to the radius. Now because of the square relationship here, that if my speed or my velocity doubles, so what we get is a 2v all squared, and we're told that of course we're going to get twice the force because we've established here this relationship here. What happens to r? Well, of course this value here becomes 4 because of the fact that we get 4v squared over this second r. But if this is twice the force, that means r has to be doubled. It has to increase so that we have a consistency mathematically speaking. So therefore the radius also increases. And so the only possible answer is B. So let's have a look at question number 14. We have a pendulum that can be used to determine the acceleration due to gravity using the relationship T equals 2 pi square root of L over G. And if you read the question, we're asked to see what the graph looks like when we compare length and period, and then have also a look at how the gravitational acceleration of Earth and Mars differ in terms of the graph. The first step is to rearrange this formula so that we can get some sort of relationship with length and period. So what we get is T squared, you'll notice I'm squaring the both sides, is 4 pi squared L over G. When I rearrange that, I get T squared over L is equal to 4 pi squared over G. But if I work out if I were to graph T squared over L, then this would give me a lovely straight line. But what I have here is that I have the period on the x-axis and the length on the y-axis. So I need to invert this. So I get L over T squared is equal to G over 4 pi squared. If I were to graph again L over T squared, in other words, if this was squared over here, this would give me a constant gradient, but I don't have that. I don't have a squared there. So as a result, I'm going to have to exclude these graphs because length versus period will not give me a linear fit based on this mathematical relationship. No, instead I'm going to get a curve. Now, which curve is it? But as you can see that the L over T squared is equal to G over 4 pi squared. If G is bigger, it's going to be a steeper curve. So the only possible answer for that is this one, because here we have a greater steeper curve the whole time compared to that over here, and of course this is Mars and this is Earth. So the answer is C. Question 15. The diagram shows a simplified model of the Michelson-Morley experiment, and it can be assumed that distances L1 and L2 are equal without affecting the outcome. And the time taken for the light to travel in both directions along the length 1 and 2 are T1 and 2 respectively. The question here, what was Michelson and Morley, of course, attempting to demonstrate in this experiment? And if you remember the experiment and you studied it, then you will know that they got a null result. In other words, they got no change whatsoever in the two paths. The relativistic contraction of L would cause T1 to be less than T2, but that's not what they were attempting to demonstrate, so A is incorrect. The ether is carried through space with Earth, which would cause T1 to be equal to T2. Now that is not correct either, because the ether isn't carried through space. The ether is a fixed frame, and Earth moves within it. And so they would expect this to be equal, but that's not the reason why. C, the times T1 and T2 would be the same. It's because the velocity of the apparatus was much less than the speed of light. That's not what they were expecting. D, the motion of the apparatus resulting from the Earth's orbital motion, which is true, around the Sun would cause T1 to be greater than T2. That's what they were expecting. By measuring the motion of the Earth as it travels through the ether, and because the fact that the motion is traveling in different directions at different times, then they expected the apparatus to get differing results of T1 and T2. So the answer becomes D. Question 16, we're now getting a little bit harder. We see a train at rest in a tunnel, and you can see that the tunnel is shorter than the train. In a thought experiment, a train is traveling from left to right, fast enough relative to the tunnel that the length contracts and it fits inside the tunnel. The observer on the ground sets up two cameras, X and Y, to take photos at exactly the same time, and the photos show that both ends of the train, like here, and you can see that the train is slightly shorter than the mountain or the tunnel. Now, a passenger traveling on a train at the center can see both ends of the tunnel and is later shown the photos. And this is important. From the point of view of the passenger, what is observed? Well, the first thing you need to understand is that the train is a constant length based on this person sitting on the train. And since the tunnel is the thing that's moving relative to the person, the tunnel's length shortens. And so the tunnel's length contracts, so the train does not fit in terms of equal. This sounds correct. The tunnel's length contracts so the train does not fit. That is correct. The tunnel appears to expand. That is not correct. And the last bit says the tunnel appears to expand. That is not correct. So we've now discounted C and D. But what about the two photos? The thing is though, if they see the photos being taken, then they're actually seeing the light of the camera taking the photos racing towards them. But in the case of the person on the train, this light here, they're going to meet ahead of this one here, because here they're moving away from the light. Remember, the light is traveling at the speed of light, and this light is traveling at the speed of light. So it's a question of simultaneity. They're going to see Y first, and then they're going to see X second. So they're going to see photo 2 first and photo 1 second. So photo 2 is taken before photo 1. A is the correct answer. Question 17, the graph shows the maximum kinetic energy of electrons ejected from different metals as a function of the frequency of the incident of light, and what can be deduced from this graph. Well, this is the classic graph where the kinetic energy of the electron emitted due to photoelectric effect is equal to hf minus the work function, which is h multiplied by the threshold frequency, which are these values right here. So what this is saying, there is a lower photon energy required for potassium, a higher one for sodium, and highest again for zinc. In all cases, the slope of these lines are equal to h. It's just that the threshold frequency is different. What can be deduced? The maximum kinetic energy of electrons is proportional to the number of photons incident on the metal surface. Well, this is exactly against the whole concept of the photoelectric effect, because it is the energy of the individual photon that determines the kinetic energy of the electron, not the number of photons. In fact, the number of photons only affect the current, which is the number of electrons per second passing through the circuit. So that is incorrect. B, more photons are required to cause an electron to be ejected from zinc than from potassium. This is again counter to what the photoelectric effect says. The number of the photons do not play a part as to whether they will be releasing electrons from the metal. It has to be related to the energy of the individual photons, HF. So B is incorrect. C, any photon that can eject an electron from a zinc surface must also be able to cause an electron to be ejected from potassium. If it releases zinc, then we clearly are at a level that is beyond threshold frequency here. Well, if that's true for that, then it's certainly true for sodium and even more certainly true for potassium. This certainly sounds correct. But let's confirm it by looking at D. For any given frequency that causes electrons to be ejected from all three metals, so we're looking at any energy at this level here, the number of electrons ejected is always greater at potassium. Again, that's about the numbers of electrons. So if I have a single photon of energy equal to something in this range over here, it will only still release a single electron from not only zinc, but also in sodium and also in potassium. It's just that their kinetic energies are going to be differing. So D is incorrect. C is definitely our answer. 18, experiment is set up as shown, and you're asked when the switch is closed, what is going to happen in terms of the current from between X and Y, and what is going to happen to the pole here. If this switch is closed, what is the direction of the current? The current always going from the positive to the negative. We're going to have a current that is going in that direction like so. If the current is going in this direction, so from the top that looks clockwise from that perspective, then the current in this situation here has to be anti-clockwise. Why is that? Because of Lenz's law. We're going to have a current going in that direction. And if you follow that process along, then we're going to have a current going from X to Y because of Lenz's law. It's got to oppose the one that changes it. Now, that means we have from X to Y and X to Y. But now what happens? Well, we here have a current going in that direction, and if you use your right-hand grip rule, that will produce a north pole here and a south pole here. Now this one here, if you use your right-hand grip rule, that will produce a north here and a south here. Again, it opposes the one that creates it. If it was the opposite, it would pull it in and it would increase the current, and you would actually violate the conservation of energy. So it has to be moving away. It repels. That means the pointer is going to be pushed up, and therefore the only possible answer is B. 19 is a little bit more challenging. The last two are, of course. We have a mass hanging from the roof of a bus that was traveling forward on a horizontal road at a constant velocity, and the string holding the mass was cut, and at the same time the bus driver applied the brakes, causing the bus to slow down at a rate of 3 meters per second, which means the acceleration is slowing down is in that direction of 3 meters per second squared. Now, to the observer on the bus, the mass follows a parabolic trajectory. It's independent of the bus, and that's what you would expect. It would do this because it would keep going at the velocity of the bus. Of course, it's separated from the bus, and so it would just follow a parabolic path. But we're asked for the resulting motion of someone observed in the bus. So relatively speaking, that ball will be moving away from them, but at an acceleration in the opposite direction. Remember, they're going, the acceleration of the bus is in this direction, so the ball will appear to accelerate at 3 meters per second in that direction. But at the same time, it is also accelerating at 9.8 meters per second squared in that direction. What is the net effect? Now, these are both accelerations, and so you're going to get here a line that looks like this. Because of both accelerations, we're going to have a linear line here. So the mass traveled in a straight line vertically downwards? No, that is not true. The mass traveled in a straight line downwards towards the front of the bus. That's what's going to happen. So that's actually correct. the mass travelled in the parabolic towards the back of the bus. Now it's not going to go in the back of the bus because the track is slowing down, so therefore you're not going to get that. And similarly in the case, it's not going to be parabolic in either case. To be parabolic, it needs constant velocity in the horizontal, and that is clearly not the case. So B is the answer. And now to the last question, which is a little bit challenging, but if you bear with me, it'll be making sense. So what we have is two galvanometers that are connected here, and we have some relative movement of the initial galvanometer, galvanometer X, and we see not only a deflection of the needle in X, but we end up seeing also a deflection in Y, and you have to explain what happens to Y and then what is the reason why that moves. The first thing to understand is to appreciate the fact that if this wasn't working as a galvanometer and we have a current flowing through it, then the current, of course, would enter at X and leave at Y. So it acts like a motor, and so we would have the needle deflect towards the right. But when we move the galvanometer body towards the left, so in other words, we're going in this direction, the needle deflects to the other way, but now it's not acting like a motor, it's acting like a generator. And so instead of the current going in at X, as you would normally expect it, the current is coming out. So we have a current going from X over here to Y. So the current is going in on the Y terminal at Y. If the current was going in at the positive terminal at Y, we would expect the needle to deflect towards the right. But because the current is going in at the negative terminal, the needle will deflect towards the left. And so automatically we can discount A and B. The answers are either C or D because the needle here deflects towards the left. The question then is why? Either C, Y behaves as a motor with the current flowing through it from right to left. Now that's correct, from right to left. Now, the next response, for every force there is an equal and opposite force. Yes, that's true, but it actually doesn't explain anything as to why it actually moves. So the answer is actually C. The needle moves towards the left because the galvanometer behaves like a motor and the current is moving through it from the right side to the left side. There we have it. Thanks for watching, and my next video will be on the short answer section of the HSC paper for Physics 2018. I'm Paul from High School Physics Explained. Bye for now.